Hello, we are MathRam team and today we will share our algorithm for the MathWorks Minidrone Competition. First, we have the image processing subsystem. The image the drone has captured at that moment is saved. Then, the image is changed from RGB format to binary format. With the processed image, we crop it in 5 segments to identify where to go. When there is a path in front of the drone, it will send a value of true in the move variable. If not, it will look for a path on both sides and apply Hop transformation to determine the rotation angle which we will send to the path planning subsystem.
Now, let's go to the path planning subsystem. The first part is the takeoff, in which the drone starts to fly by changing only the z-axis. Once the drone is in the air, it makes a decision between going on one of the two states turn around and go straight, based on the variable of move, angulo, and low. On state turn around, the angle yaw is changed proportionally depending on the value of angulo. On state go straight, the drone moves on the x and y axis. Also, it switches between a fast and slow mode depending on the low variable. The valuables held during these two processes are the coordinates x, y, and z, and the value of yaw. For the landing strategy, we count the number of changes between both states. When this counter reaches 100 times, the landing state is activated.
The first challenge we faced was landing. For landing, it started descending fast until it reached minus 0.01. The drones start descending slower to ensure a safe landing. Also, while landing, the drone adjusts of values x and y to ensure a correct landing in the center of the red circle.
Second challenge, velocity. At first, we developed a version 1 model to accomplish the goals proposed by the competition. The next step was to make it better, adding some features. The most notable opportunity area was the time it lasted. This previous model was very slow, but the trajectory that it showed was smoother. We had to find a balance between time and precision. Therefore, we started to experiment with different velocities and our path landing system. This took us to our next challenge. The inertia suffered in corners due to this increase in velocity.
Third challenge, inertia in corners. The third challenge we faced was the inertia in corners. This happens because the drone moves fast. When it's time to turn around, it goes further than it should, which makes its position not coincide with the expected value. This is solved by putting the value of x and y with the values of x estimated and y estimated. This makes that when it's turning around, it also adjusts its position. This results in trajectories like this. We can see an example of these spins in action. With this model, we accomplish the characteristics specified by the competition in the ambits of the image processing and path planning of the drone. Our model is capable to recognize the path and decide where to go combining movements in x and y axis, but also rotation respect to that z axis. Also, it is able to land at the red circle of the end. We are conscious about our landing process is not the best way to do it because it doesn't imply recognition of circles or another complex way. But our approach is useful and have valid results. Thanks to this competition, we'll learn a lot about image processing and the use of Simulink, especially in state flow. This applies in situations related with systems that interact with the real world. This results in a benefit for us because we are starting to use these tools in our formation as engineers. Also, the programming of drones gave us a new perspective of projects that we could develop in a future with more ambitious goals.